welcome everyone to today's row. It's my pleasure to introduce Esther as the first speaker of the junior row. So Esther is a PhD student at Technical University of Delft. Her research is on the intersection of machine learning and robust optimization or optimization in general. And today she's actually going to talk about machine learnings and how we can use it in K-adaptability approach. So without further ado, the mic and screen is yours, Esther.
Yes. Yeah, thanks for inviting me. Okay, so today I would like to talk a bit about my project, which I finished, I think, more than a year ago already. And it's on machine learning for K-adaptability in two-stage robust optimization. So first, I want to just give a short introduction to robust optimization. Okay, let's see this graph in which you want to find the shortest path from the source to the target. And for example, this could be like this could be the shortest path for this example. But yeah, maybe there's like a traffic jam or something happening. So there's like uncertainty, and then you maybe would like to go in via another path. So like this. One way of solving these kind of problems, like under uncertainty, is with robust optimization, in which you solve for the worst case scenario. So here we have the decisions of X. They can be whatever, they can be like continuous, integer. And then here we have the adversarial problem. So we try to minimize, and our adversarial is trying to get the worst objective value. And then what we were working on is in two-stage robust optimization. So you have to make a decision before and after a so-called realization of uncertainty. So this Z is the scenario. And the X is first stage, the second stage is the Y, and then the Z is the uncertain scenario in an uncertainty set. And ideally, you would like to solve both X and Y at the same time, because there can be some dependencies between the two stages. But because in the second stage, in reality, you do know what has happened, you would like to adapt to your realization of uncertainty. So let's go back again to the same graph. Maybe a city planner would like to make the area a bit more livable. So maybe a city planner wants to shut off some streets. This can be a first stage decision. And then after some kind of, the uncertainty is realized, you would still like to get to your target as fast as possible. And then this could be your solution now. So here you see like X was closing some streets, and Y is getting a shortest path. These kind of problems are can be formalized as a min-max-min problem. So the X is the first stage, the second stage is Y, and Z is your adversarial problem. This problem can be approximated with K-adaptability, such that you have K second stage decisions that can adapt to subsets of the uncertainty set. And these subsets can have different forms. They can look different. As you can see here, you can split it either in this way, or like an infinite number of other ways. So this in itself is also a very difficult problem. And the K-adaptability problem is formulated like this. So note that in the first stage, you have your first stage decisions and K copies of your second stage decision. And then you have your adversarial, and then you have to decide in the second stage which of these K decisions is the best. And then note that for every optimal X and YK combination, there is an optimal subset ZK in Z, and the uncertainty set. So what the algorithm, the K-adaptability branch and bound algorithm does is iteratively splitting this uncertainty set and then finding the best X and YK for each of these subsets. Okay, so let's first introduce this problem, this algorithm. This was work done by Subramanian et al. In 2020, and it works like as follows. First, okay, so let's just consider again the problem. You can change this problem into more a level set, I believe it's called, formulation, in which we have a finite number of scenarios in our subsets. So, and they are initially empty. So when you solve this problem, you only have to look. So you only look at a subset of all the scenarios, and then you solve a subproblem that finds a violating scenario for your current solutions of your master problem. And then you add this scenario to any of the subsets. And then you continue on like this until you find a robust solution. However, as you may have already noticed in the add scenario phase, you can add it to any subset. So yeah, maybe adding the scenario to one problem or to one subset or the other can be a lot better. And this is described as a tree. So in each node, you solve your master problem, then you find your violating scenarios, Z1 in this case, and then you add it to one of your subsets. And yeah, in the first stage, it doesn't really matter if you have it to the first one or the second one. So you can just ignore the other node that you would have created. But now Z2 is violating for this node, and you can either add it to Z1 or add it to the other subset. And this is for k is equal to 2. But when you have, when k increases, then you also get k child nodes. So this tree can explode quite rapidly because the width is determined by k. And also, if you need many scenarios in order to get a robust solution, then you can get a very very deep tree as well. So ideally, with these kind of problems, you would like to go to the optimal nodes directly, because otherwise you have to spend a lot of time in exploring many of these nodes, many different objectives. Okay, so now what we were actually doing in the machine learning part. I first want to explain what you have to predict, and then also how to get your training data, because that's often with this kind of combinatorial and optimization methods one of the most expensive parts. And then usually you have to also decide on which machine learning model you want to use, and we just use a random forest without any tuning from scikit-learn. Okay, so node selection with machine learning isn't really a new thing, of course. It has been done by a few other papers, but mainly for branch and bound in mixed integer linear programming. And we are doing it, I think, for the first time in robust optimization. And also, we are really looking at what it means to go from one node to the other in terms of the scenarios. So we are really trying to make use of what it means to add a scenario to another subset. Okay, so our approach is as follows. In each iteration, you okay, sorry. We want to predict per parent and child pair if it will be a good idea, to traverse in this direction. And then in each iteration, you do this for all of your K different childs. So it's a depth first approach. And so if you can see, like for P, this node is labeled PK1 L3 because it's on the third level. And this one, it should be less than this one. And if this is the case, then we traverse to the optimal solution faster, if all training and everything is going correctly. So we want to make sure that our P values, so these success probabilities, follow the optimal path. Okay, and what is the input of the machine learning model? We have two different kind of inputs, two different kind of features. One are the state features, and two are the scenario features, which I want to talk about later. The state features just give some kind of description of where we are at in the tree. And this is, the depth of the current node, objective value, violation value. So how far off the scenario that we found in the subproblem, how much the constraint was violated with this scenario. And then also we have the scenario attributes, so the scenario features. So per scenario, we give it some kind of information. So for example, the value of the scenario itself, but also how this scenario, what the X and the Y and the objective would have been if we only considered this scenario. And we think that maybe there could be some, it could be a good measure for the differences between these attributes. So how far away our new scenario is from the subset we want to add it to. So actually not for this one, sorry, it's for this on this side. So if we would like to add Z8 to, oh no, sorry, it is. If you would like to add Z8 to Z2, Z4, so then going this direction, then it could be interesting to look at the differences between the attributes. So then we take the mean, for example, of the attributes in the subset is already in, and then take the distance between the mean and the attributes of the new scenario. Okay, and then the training data. If you would have known the entire tree, which is too much, of course, because it's not possible, then it would have been easy to label the success probabilities of each node. So then you would know how well, how good it would have been to traverse through this node if you would have known the entire tree. But this is of course not possible. So what we do is we stop at a certain level and then do some kind of Monte Carlo tree search approach to determine the success probabilities of the nodes in this level. And how we do this is with like random dives, so like a simulation, and then gather all of the objective values that we have encountered, and then look at which ones were better or worse. And this determines the level of the probability of success of these nodes. And then how we continue is we backpropagate these probabilities to the root of the tree. And this is our way of labeling the nodes. And yeah, as you maybe realize now, we only focus on the top part of the tree. And I think this is a fair assumption to make, as the directions you choose in the top of the tree are the most important. Okay, so yeah, let's see, in time experiments. We applied this problem to this method to two problems: the capital budgeting with loans problem, which is a problem that has mixed integer first and second stage decisions, and a shortest path problem that only has second stage decisions in our problem formulation. And the random forest we trained was based on 20,000 data points, which is not so much. I just checked it, and I think for the revision we may want to increase it a bit. But the data generation was only 2 hours in total, so you can also parallelize it on a bunch of different nodes. So it doesn't really take 2 hours for yourself. Okay, let's go to capital budgeting. So this problem decides on which projects you want to invest. So you can either do this before the revenue and the costs are completely known, or after. But if you do it after, then it's at a certain cost. Yeah, so when you do it after, then you can only have a fraction of the actual revenue. And this is at a, so you can only invest given a certain budget, and you can increase your budget by loans. Yes, so these are the results that we obtained over the runtime of the K-adaptability algorithm. So here you can see that we stopped after 30 minutes, I believe. And the K-adaptability branch and bound with node selection, so our new approach with the machine learning selection, is given in red. So this is the median across 100 instances, and the shaded area around it is 75% quantile. And this is the relative objective function value compared to what the random, so just K-adaptability with random node selection, achieves after 30 minutes. So that's why it goes to 1 as well. And you can see that especially in the beginning with our approach, our node selection rule, the increase is a lot faster. And this is based on training and testing on the same instance size. So n is equal to 10 for this problem, and a value of k is also the same. And we can apply this, we can train on one model with different sizes of, with different instance sizes, and apply it to others. And I will talk about that later actually. But we can also apply, because we just make one prediction per child node. It doesn't matter on how many values of k we trained. We can apply it again to bigger values or smaller values. So here we train actually on different values, and we apply it to k is equal to 5. And you can see that especially when training on higher sizes of k, higher values of k, the machine learning model is performing better. And then here, as I already mentioned before, we trained on n is equal to 10, and we apply it to bigger values of n. And the results don't always look amazing, to be honest, but for n is equal to 10 and k is equal to 4, it gives similar results as before. But here, the confidence interval is quite large, so it's not really stable, I would say. We also applied this problem, or applied our algorithm to short path problem, so only with second stage decisions, and the uncertainty lies in the length of the path. And yeah, here we only have second stage decisions, but if you rewrite it again into K-adaptability formulation, then these Y copies are in the first stage, and then you have to decide in the second stage which K you select. Here we see the same kind of results as before, for the same instance size and K value. And here we see, similar results. So it drops down earlier. especially for k is equal to 3 in this case. And if we train on different values than we apply it to, we also get similar results as before. However, for when you apply it to higher instance sizes, then yeah, the results are like random, or our methods are almost as good. So we don't really see a significant improvement there. Okay, so just to wrap up, we want to speed up K-adaptability branch and bound with ML informed node selection. We do this in each iteration. We do this to make a prediction for each of our child nodes, and then select the highest value. And we get our training data by a kind of Monte Carlo tree search approach. Okay, thank you.